Good morning, all of you. My name is Sai Kiran. I'm your chemistry lecturer. If you remember, in our last class, we discussed detailed explanation of Bohr's atomic model. Today, we shall be discussing about development towards quantum mechanical model of atom. We have two major developments. One is deBroglie's wave theory, and second one is Heisenberg uncertainty principle. Now, we will start with deBroglie's wave theory. This theory explains dual nature of matter. We know that light have dual nature. That is, one is wave nature and second one is particle nature. Similarly, according to this theory, all microscopic particles like electrons moving with high velocity, it associated some wave nature. Let's understand. This is a microscopic particle. It has some mass moving with high velocity, v. It associated some wave nature as well, like this. This wave has some wave properties like wavelength. And this particle also associated with some linear momentum, that is P. We know that P is equals to product of mass into velocity, mv. And according to Einstein mass energy, E is equals to mc square. And according to Planck's quantum theory, E is equals to hc by lambda. From these two results, we get mc square is equals to hc by lambda. From this, lambda is equals to hc by mc square. Square c gets cancelled. Lambda is equals to h by mc. In this, c is the velocity of light. He replaced c with velocity of moving particle. He gave a result relation between wavelength and the momentum of moving particle. That is, lambda is equals to h by mv. Or lambda is equals to h by p. Here, lambda is the wavelength, m is the mass of electron, v is the velocity of electron, h is Planck's constant. That equals to 6.625 into 10 to the power minus 34 joule second. And p is the momentum of a moving particle. This theory is applicable only for a microscopic particles like electron, proton, alpha particle, etc. In case of macroscopic particles, the wavelength is very negligible. Very small, so negligible. We can't determine the wave properties. Let's understand. In this, we consider the relation between wavelength and mass. Wavelength is inversely proportional to mass. It indicates mass is less, wavelength is more. When mass is less, for microscopic particles, mass is very less. So, wavelength is more. When wavelength is more, we can determine the wave properties. In case of macroscopic particles, mass is more. When mass is more, wavelength is less. When wavelength is less, it is negligible. So we can't determine the wave properties. For example, this marker is a macroscopic particle. It moves in a direction. It associates some wave nature. But this is a macroscopic particle. Mass is more. So wavelength is less. So wavelength is negligible. Now come to the de Broglie's concept with Bohr's model. De Broglie's result is lambda is equals to h by mv. And one of the Bohr's result is mvr is equals to h by 2 pi. Two types of waves are possible when an electron is moving around the nucleus in a fixed circular path. For example, this is nucleus and this is fixed circular path. One wave is stationary wave. This is like this. This is called stationary wave. In this case, electrons revolve in this wave only. Only one wave is possible. In this case, the circumference is 2 pi r. Circumference of orbit. That is equals to the n lambda, number of wavelengths. From this, we know the lambda value. Here, put this lambda value into this formula, we get 2 pi r is equals to n into h by mv. This mv comes this side, this 2 pi comes this side, mvr is equals to nh by 2 pi. This is the result of Bohr's model. Hence, de Broglie's concept is agreed with Bohr's model. Now come to the second wave. Non-stationary wave. This wave like this. In this, there is another possibility to form one more wave. In this case, the circumference 2 pi r is not equals to the n lambda, number of waves. So, such type of orbit cannot exist. Now, come to the applications of de Broglie's wave theory. First application is the number of waves formed in an orbit is equals to the n. So, in case of first orbit, one wave is formed. In case of second orbit, two waves are formed. In case of third orbit, three waves are formed. And second application is, it is very important. The relation between kinetic energy and the wavelength of moving particle. That is, we know the formula lambda is equals to h by mv. And we know the kinetic value. Kinetic energy is equals to the half m v square. Now, I am multiplying this side m divided by m. This 2 gets cancelled, we get same value. Now, kinetic energy is equals to half m square v square by m. This 2 and this m comes this side. 2 times kinetic energy into m is equals to m square v square. This square comes this side, it will convert to root. 2 times kinetic energy into mass, that equals to mv. This mv value is substitute in this formula, we get lambda is equals to h by root of 2 times kinetic energy into mass. This is one of the important result. Majority of questions asked on this formula. And now come to the third application. If a charged particle like electron accelerated with some potential V, then change in kinetic energy is equals to charge into voltage applied. Let's understand. This is a charged particle. Charge is E. Now I am supplying some voltage. Then it starts acceleration. Initially, the kinetic energy is 0 because there is no movement on this charged particle. When we supply some voltage, it starts move. Now it has some kinetic energy. This is final kinetic energy. The change in kinetic energy is kinetic energy final minus kinetic energy initial. That equals to charge into voltage applied. Kinetic energy initial is 0. So kinetic energy is equals to E into V. Substitute this kinetic energy value into this formula, we get one more result. That is, lambda is equals to h by root of 2 times electron volt m. This is one more important result. In this, lambda is wavelength, h is Planck's constant, E is charge of electron, V is voltage applied, m is mass of electron. For an electron, de Broglie's wavelength is equals to 12.27 by root of V angstroms. For a proton, de Broglie's wavelength is equals to 0.0286 root of V angstroms. For a alpha particle, de Broglie's wavelength is equals to 0.101 root of V angstrom. Here, the V is voltage applied to the charged particle. And next application is the de Broglie's wavelength of an electron in a given orbit is equals to 3.33 into n angstroms. Here n is the orbit or shell. This is the de Broglie's wave theory. Now come to the Heisenberg uncertainty principle. According to this principle, it is impossible to determine the position and momentum of a microscopic particle like electron simultaneously and accurately. Let's understand. This is nucleus and this is orbit. Electron is present here. Before this, we discuss a simple concept, that is one of the property of light, that is reflection. We know that reflection is nothing but when light falls on an object that reflects to our retina, then only we can see that object. Like this, we want to the position of this electron with the help of microscope. When light falls on this electron, then only we can see. But in the same way, the electron absorbs energy from the light and the velocity or momentum of the electron is changed. That is, we want to measure the position, error occurs in the velocity. We want to measure the velocity or momentum, error occurs in the position. That is the Heisenberg uncertainty principle. The mathematical expression for Heisenberg uncertainty principle is delta x dot delta p greater than or equal to h by 4 pi. We know that p is the momentum that equals to mass into velocity. So, delta x into delta mv greater than or equal to h by 4 pi. Here, m is the mass is constant. So, delta x dot m into delta v greater than or equal to h by 4 pi. From this, delta x into delta v greater than or equal to h by 4 pi m. This is one more result. In this, delta x is the uncertainty in position and delta p is the uncertainty in momentum and h is Planck's constant. Here, delta v is the uncertainty in velocity. M is the mass of electron. If we want to determine the exact position of electron, now electron is present here. Exact position of electron is here. Now change in position is equals to 0. From this, delta v is equals to h by 4 pi m into delta x. Now delta x is 0. This term, total term is 0. Anything by 0 is equals to infinity. Now delta v is equals to infinity, which means uncertainty in velocity is infinity. Similarly, if we determine the exact momentum of a electron, that is delta p is equals to 0, the uncertainty in position is infinity. And this is applicable for microscopic particles. In case of macroscopic particles, Let's consider the relation between uncertainty and mass. That is delta x into delta v inversely proportional to the mass. If mass is less, uncertainty is more. So we cannot determine the position and momentum simultaneously and accurately. In case of mass is more means macroscopic particles. Uncertainty is less. Now we can easily identify the position and momentum of a macroscopic particle simultaneously and accurately. Further, we can easily measure the NASA said rocket after some time rocket is here and the momentum or velocity of rocket is that much. That is the example for this macroscopic particles. So this is only applicable for microscopic particles. And according to Heisenberg, we can only determine the probability of finding electron. We cannot determine the exact position of the electron. For example, electron is right here, electron is right here, electron is right here is wrong. At this point, Bohr's theory was failed. According to Bohr's theory, electrons revolve around the nucleus in a fixed circular path, which means electron is present here or here or here. This is wrong. According to Heisenberg, there is a probability like this. In this, probability of finding electron is maximum. Maybe electron is present here, maybe electron is present here, maybe electron is present here, maybe electron is present here. We can't say exactly electron is present here. It is just a probability. Now, new term was introduced, that is orbitals. This term was developed by Schrödinger with his quantum mechanical model of atom. That's it today class. In our next class we will discuss quantum mechanical model of atom.